What does it take for workers to call their own workplace a guaranteed killer? By 1880, Standard Oil's Cleveland refinery was the largest on Earth, pushing 25,000 barrels a day across 90% of America's refining capacity. Inside, wooden tanks swelled against iron hoops. Naphtha vapors with a flash point barely above body temperature pooled along the ground, feet from open flames beneath crude stills. One leaking seam, one overheated valve, and a 12-hour shift became a race against fire no man could outrun. These refineries fueled a nation's hunger for cheap kerosene, but the mechanics that made them productive earned them a name whispered like a curse. The forces behind that deadly design have never fully disappeared. By the late 1870s, the United States was lighting up at a pace no country had seen before. Cities doubled in size within a generation, and the sun no longer set the rhythm of American life. Kerosene, once a luxury, became the fuel of choice for millions, its blue-white flame burning in every parlor, shop, and street lamp from New York to Chicago. In 1865, fewer than 10,000 barrels of refined oil moved through Cleveland each day. 15 years later, Standard Oil alone pushed out more than twice that, flooding the market with cheap, steady light. The numbers told their own story. Between 1870 and 1880, the price of kerosene dropped by more than half. Where a gallon once cost over 30 cents, it now sold for less than 15 cents. That shift powered a boom in urban growth. By 1880, New York's population topped 1.2 million, and Cleveland's tripled in just 2 decades. Households that once rationed whale oil or tallow could now afford to keep lamps burning through the night. Factories, rail depots, and saloons stayed open late, their windows glowing with the promise of progress. The appetite was insatiable. Standard's Cleveland refinery alone processed 25,000 barrels every day, enough to fill a line of rail cars stretching for miles. Across the country, demand for kerosene outpaced any other refined product, and every corner grocer kept it in stock. The push for cheap lighting was relentless, and the market punished any company that failed to keep pace. Refiners raced to expand capacity, cramming more tanks, stills, and piping into every available lot. Output soared, but so did the hidden risks. Each new barrel shipped out meant more heat, more pressure, and more volatile vapors packed into yards that left no room for error. This national hunger for light set the terms. Efficiency and volume became the only measures of success. The refineries that powered America's nights did so by shaving margins to the bone, accepting hazards as the cost of doing business. The dangers that lurked behind those glowing windows were not a secret. They were the price of progress. Cleveland and western Pennsylvania did not rise as refinery capitals by accident. Geography and logistics dictated their fate. Cleveland, perched on the southern shore of Lake Erie, sat at the crossroads of America's energy surge. Railroads stitched the city to the Pennsylvania oil fields, with lines like the Lake Shore in Michigan's Southern and the Atlantic and Great Western funneling crude in a steady stream. Barges and tank steamers moved oil across the lake, docking at waterfront yards within sight of downtown. By 1880, more than a dozen major rail junctions converged in Cleveland, turning it into the nation's busiest inland oil terminal. Pennsylvania's refineries clustered along the Allegheny and Oil Creek valleys, close to the earliest gushers. Crude from fields around Titusville and Oil City traveled by wooden pipelines and gravity-fed troughs, then loaded onto the Pennsylvania Railroad. The proximity to supply meant refineries could process oil just days after it left the ground. Standard Oil's strategy was simple: control every step from wellhead to lamp. Cleveland's yards sprawled for blocks, packed tight against the Cuyahoga River and the rail sidings. Pennsylvania's plants, hemmed in by hills and riverbanks, squeezed tanks and stills into every available patch of flat ground. The physical layout was a product of relentless demand, yards designed not for safety, but for maximum throughput. Crude arrived by the trainload, storage tanks rose in clusters, and distillation sheds lined up shoulder to shoulder. The map of these sites reads like a warning. In Cleveland, Standard's Excelsior Works and neighboring refineries formed a dense industrial belt with only a few muddy lanes separating tanks from the city's neighborhoods. In Pennsylvania, wooden storage farms and boiler houses pressed up against worker cottages and main streets. There was no buffer zone, no engineered containment. The same tracks that brought in crude could carry disaster straight into the heart of town. Every barrel refined in these hubs powered the nation's lights, but also raised the odds of catastrophe. The danger zones were not hidden. They were mapped into the daily life of Cleveland and Pennsylvania, where a single spark could turn progress into tragedy. Expansion was relentless. In Cleveland, Standard Oil's yards multiplied almost overnight. Between 1875 and 1885, daily capacity at the city's main refineries jumped from less than 15,000 barrels to more than 25,000, a staggering leap that forced every inch of ground into service. Pennsylvania's plants followed the same pattern, crowding new tanks and stills wherever a rail spur or creek bank allowed. The pressure to deliver more kerosene, faster and cheaper, left no time for careful design or upgrades. Old tanks stood side by side with new ones, their seams strained by the constant flow. Wooden storage farms, once spaced for safety, became dense forests of barrels and iron hoops, each one a potential fuse. Workers watched as yards filled with new equipment, but the basics never changed. Walkways narrowed, leaving less room to maneuver. Steam engines, bought secondhand, ran hotter and longer, their sparks a constant threat. Boiler houses pressed up against storage sheds, sharing walls and even roofs. There was no master plan, just a race to pack in more machinery, to squeeze out another 1,000 barrels before the next competitor caught up. By 1880, Standard Oil's Cleveland operations alone processed more than twice the crude of all its local rivals combined. Across the refining belt, output soared from a few thousand barrels a day in the late 1860s to more than 40,000 by the mid-1880s. But for every new tank or still added, the risk multiplied. The same rail lines that delivered crude now ran through crowded yards, their iron wheels sparking against stone just yards from open vats. Rainwater pooled beneath the tanks, mixing with oil to form slick, invisible channels that could carry fire the length of a property in seconds. The drive for scale left little margin for error. Pressure gauges, already unreliable, were pushed past their limits. Valves and joints strained under loads they were never designed to bear. Few workers had time to learn new routes or spot fresh hazards. The layout changed as fast as the demand. In the rush to keep pace with America's hunger for light, the line between routine and catastrophe grew thinner each year. The promise of progress was measured in barrels, but the cost was paid in risk that grew with every new expansion and that no one could truly control. Beneath the surface of Standard Oil's success, every barrel of kerosene depended on a chain of hardware that was never built for certainty. The most basic link, the storage tank, was a compromise from the start. Tanks meant to hold thousands of gallons were built from thick wooden staves, bent into shape and cinched tight with iron hoops. These hoops were not ornamental. They fought a losing battle against the daily forces inside, swelling as summer heat pushed the wood to its limits, shrinking in winter until gaps appeared at the seams. Each tank was a living thing, flexing and breathing with every shift in temperature or pressure. Engineers of the era calculated hoop tension by rule of thumb, not by science. A tank filled to the brim with crude or naphtha pressed outward with tons of force, but the iron bands could only hold so much before the wood began to bulge or the seams to weep. When pressure spiked after a sudden rainstorm cooled the tank, or a new batch of warmer oil was pumped in, seams sometimes split with a sound like a gunshot. Even when nothing burst, slow leaks were constant. Oil seeped through hairline cracks, soaking the ground, and vapors escaped invisibly through every imperfect joint. Riveted iron tanks, a newer alternative, offered little improvement. Each seam was a line of potential failure. Rivets stretched and loosened under the daily cycle of filling and emptying, and the thin plates flexed with every pressure change. A poorly set rivet could pop free, turning a minor drip into a jet of flammable spray. Maintenance was mostly reactive. Workers patched leaks with whatever was at hand, scrap wood, tar, or rags, never truly sealing the breach. Valves and fittings, made from cast iron or brass, added their own risks. Threads warped from heat and vibration, and joints loosened until they hissed with escaping vapor. The smallest leak could create a cloud of fumes heavy enough to blanket the ground, waiting for a spark. Containment was an illusion. Rain pooled beneath the tanks, mixing with oil to form slick, reflective sheets that snaked through the yard. There were no berms, no concrete dikes, just mud, weeds, and the hope that nothing would go wrong. Every tank, every seam, every valve was a silent gamble. The equipment was not built to last, only to keep pace with the next trainload of crude. In this world, failure was not a rare event. It was the background hum of daily life, a constant threat that could turn routine into disaster with no warning. Heat and vapor were only half the equation. Every refinery yard in Cleveland and Pennsylvania bristled with ignition sources, each one a silent threat hiding in plain sight. The most obvious was fire itself. Distillation stills sat atop brick or stone hearths, their bellies licked by open flames that could reach over 1,000 degrees Fahrenheit. Workers fed coal or wood into these fires by hand, judging the right moment by the color of the flame or the sound of boiling oil. There was no automatic shutoff. If a batch ran hot, the only warning might be a sharp hiss or the sudden metallic scent of vapor escaping from a seam. Pressure gauges, when present at all, were unreliable. Many stills operated with missing or broken dials, leaving men to guess at the forces building inside. A stuck needle or fogged glass turned routine into roulette. If pressure rose too fast, a still could rupture without warning, hurling hot oil and metal across the yard. Even when the equipment held, the heat underneath stills and storage tanks baked the ground, drying out wood and loosening joints until vapor seeped through every gap. Pressure was a constant, unseen danger. Mechanical friction added another layer of risk. Steam engines, often bought second-hand, drove belts and pulleys throughout the plant. Leather belts whipped over iron wheels day and night, their friction building heat with every revolution. A loose belt could slap against a metal guard, striking sparks, invisible in daylight, but deadly in a yard thick with fumes. Grainy dust from coal and oil settled on every surface, waiting for a static discharge or a carelessly dropped tool to set it alight. Friction created hazards that no checklist could fully eliminate. Lighting was a hazard in its own right. Lanterns, sometimes open flame, hung from beams or sat on oily planks. Even a single knocked-over lamp could send fire racing across a slick floor. Smoking was officially banned, but in practice, men sometimes lit pipes on break, their embers glowing just feet from vapor clouds. In the still houses, the air itself could become explosive. It took less than 1/10 of a joule for a spark too small to see to ignite the right mix of air and naphtha vapor. Every day, workers moved through this web of threats. They learned to sense when the air felt heavy or when a machine ran hot, but instinct could only do so much. The refinery's design left little room for error. A leaking valve or a missing gauge was not just a nuisance, it was a loaded gun, cocked and waiting for the smallest spark. In these yards, the line between routine and disaster was measured not by plans or precautions, but by the luck of the shift and the physics of combustion. At first glance, a refinery yard on a quiet morning could seem almost peaceful. Tanks stood still, the air hung heavy with the faint tang of oil, and the only motion came from workers moving between rows of equipment. Yet beneath that calm, danger gathered in ways no eye could track. The real threat was not always fire or broken machinery, but the silent drift of vapors, fractions of crude with minds of their own. Naphtha, one of the lightest cuts, could turn from liquid to vapor at just 40 degrees Celsius. Kerosene, the main product, held out until around 60 degrees Celsius. That gap in flashpoints was more than a technical detail. It was a daily gamble. As the sun rose and temperatures climbed, naphtha began to evaporate inside tanks and pipes, building invisible pressure with every passing hour. By midday, the air just above the ground could be thick with fumes, heavier than air, pooling in low spots and creeping through cracks. A valve that seemed tight at dawn might start hissing by noon, driven by nothing more than the day's heat. These vapors did not rise and vanish. Instead, they hugged the earth, slipping under doors, collecting in trenches, and hiding beneath catwalks. A worker could cross the same patch of ground a dozen times, unaware that with each trip, the air grew more dangerous. On cool mornings, vapor might linger unnoticed until the afternoon sun coaxed it into motion. The difference between safety and disaster could be as slight as a shadow passing over a pressure gauge or a cloud drifting across the sun. Thermal stratification, the way heat layered the air, meant that vapors did not mix evenly. Hot, light gases floated above cooler, denser ones, creating pockets of explosive air that shifted with every breeze. Even a brief temperature spike could send pressure surging inside a tank, enough to force vapors through the smallest seam. There were no alarms, no sensors to warn when the threshold had been crossed. The only sign might be a faint shimmer in the air or a sudden headache, both easy to ignore in the rush of the shift. By midday, all the forces of chemistry and weather combined. Tanks strained, valves sweated, and the yard became a patchwork of invisible hazards. It only took a single spark, a dropped tool, or a slip of friction from a passing belt for the entire cycle to flip from routine to catastrophe. In these moments, the refinery revealed its true nature, a place where ordinary conditions could, without warning, become fatal. The risk was never just in the machines or the flames, but in the very air itself, shaped by forces no worker could see and few could escape. A 12-hour shift began before dawn and ended long after the air had thickened with fumes. Men filed into the yard, boots slick with oil, faces set for another day threading between tanks, stills, and engines that could betray them at any moment. There were no uniforms, just patched shirts, kerchiefs tied over mouths, and hands already stained by last week's work. Each man carried a mental map of the yard, which catwalks felt soft underfoot, which valves hissed on hot days, and where the quickest way out might be if the air suddenly turned sharp and metallic. Routine meant hauling coal to the still house, checking the color of flames under the vats, and listening for the subtle shift in the engine's rhythm, the difference between a steady thrum and the warning rattle of a belt about to slip. Lunch was eaten on upturned barrels, sometimes in the shadow of a tank that creaked as the sun climbed. The smell of kerosene never left the skin. By midday, headaches crept in, eyes burned, and throats tightened from hours spent breathing vapor-laced air. Some men learned to recognize the signs, a sudden wave of nausea, a dull ache in the chest, or a cough that lingered long after the shift ended. These were not rare complaints, but the background noise of refinery life. Burns were common. A splash from a leaking valve might scald a forearm. A careless step near a steam vent could leave skin raw for weeks. The yard's first aid was crude, rags soaked in cold water, a smear of lard, maybe a strip torn from an old shirt. Most injuries went unreported. Missing a shift meant lost wages, and few could afford that risk. There were no drills, no posted escape routes. When the alarm sounded, if it sounded at all, men relied on instinct and memory, sprinting through mazes of tanks and pipes where a wrong turn could mean running straight into a wall of flame. Every worker knew someone who had not made it out. The refinery's promise of steady pay came with the unspoken cost of constant vigilance. For those inside the gates, survival was a matter of habit, luck, and the hope that today would be just another ordinary day. When fire broke out in a refinery yard, the difference between a close call and a mass casualty often came down to what was on hand and what was not. The first line of defense was painfully basic: barrels of sand and leather buckets, each holding barely 12 liters, stationed along walkways and at the corners of tank farms. Workers trained their reflexes to these tools, knowing that a single overturned lamp or a burst valve could send flames racing over oil-soaked ground. Buckets were filled, passed hand to hand, and hurled onto slicks that burned faster than water could quench. Sand, meant to smother the blaze, clumped and scattered, barely slowing fire that leapt from puddle to puddle. Water, the universal answer for most fires, became a liability in these yards. Oil floated, spreading the flames wider with every splash. Volunteer brigades, often drawn from the surrounding neighborhoods, arrived with horse-drawn pumps that could deliver a narrow stream if they reached the site in time. Even at full force, these pumps produced a fraction of the water needed to contain an oil-fed inferno. A single horse engine might manage a few hundred liters per minute, but against a tank rupture or a burning trench, that effort vanished in steam and smoke. There were no chemical foams, no pressurized hoses, no coordinated command. Each man acted on instinct, shoveling sand or swinging a bucket in the hope of buying precious seconds. When flames jumped containment, the only real strategy was retreat. Fire lines broke as smoke thickened and heat drove men back. Oil fires moved unpredictably, following the path of least resistance, downhill, through drainage ditches, or across wooden planks, turning escape routes into traps. The mismatch was stark. The hazards of the refinery were industrial in scale, but the firefighting response belonged to a different era. Even the best-equipped brigade was outmatched by the speed and ferocity of a full-scale blaze. The result was a grim calculus. Every fire threatened not just property, but lives, and the odds were seldom in the workers' favor. Inside the refinery gates, every decision tilted towards speed and volume. Company ledgers tracked barrels and output, not injuries or near misses. Standard Oil's paychecks, steady but rarely generous, were still better than most factory or mill jobs in Cleveland or the valleys of Pennsylvania. In 1880, a refinery laborer earned about $8 to $10 a week, a shade higher than the going rate in the steel mills. For many, this was enough to keep food on the table, but not enough to walk away. The job market tied workers to the yard, knowing that a missed shift meant a missed meal and that replacements waited at the gates. The economics of the industry locked the hazards in place. Refinery yards were packed tighter each year, not out of carelessness, but by deliberate calculation. Every extra tank squeezed onto a muddy lot, every still wedged between storage sheds, translated into more kerosene for the market and more revenue for the company. The average density of tanks in Cleveland's main yards reached as high as 1 per 300 square feet, a figure that left little space for fire breaks, let alone escape routes. In Pennsylvania, the story was the same. Clusters of wooden tanks pressed up against rail sidings and worker cottages, with only a narrow lane separating flammable stockpiles from the rest of town. The company's priorities were clear. Safety upgrades such as wider spacing, stronger tanks, and better ventilation were seen as costs, not investments. Insurance premiums ran high, but Rockefeller preferred to self-insure, counting on scale and luck to absorb the losses. The logic was simple: a fire might destroy a yard, but the business could recover faster by rebuilding than by slowing production for safety's sake. Workers bore the brunt of this calculation, trapped by the promise of steady pay and the threat of unemployment. The system did not need to be cruel to be deadly. It only needed to reward output, ignore the risks, and let the rest fall where it may. The result was a refinery culture where danger became routine and where the margin between a normal shift and disaster was measured in inches and minutes. The same forces that lit America's nights created a workplace where survival depended less on planning than on instinct, luck, and the hope that the next spark would not find its mark. At 6:42 in the morning on February 13, 2026, a missile tore into Haifa's main refinery, rupturing 3 tanks packed with over 50,000 barrels each. Flames leapt containment berms and ignited a 4th tank by radiant heat. Incident commanders watched as fire breached tank shells in under 10 minutes. The blaze raged for 19 hours, devouring nearly 200,000 barrels before crews could cut off the fuel. Investigators pinpointed a direct kinetic hit as the ignition, but it was vapor clouds pooled overnight that turned a single strike into a runaway fire, an old hazard unchanged by time. On January 27, 2026, Mina Al-Ahmadi in Kuwait faced a drone strike that punctured Tank 12's roof, releasing a surge of naphtha. Vapors drifted into a pump house where a motor sparked during shutdown. Fire engulfed 4 tanks in less than an hour. Crews battled until dawn, but the yard's tight layout trapped heat and smoke. By sunrise, 6 tanks had collapsed, wiping out nearly a quarter of the site's storage. The ignition was mechanical, but the fire's spread matched the worst-case models from decades past. Just days later at Mina Abdullah, a coordinated strike on February 1st ruptured a transfer line feeding the main distillation unit. Product flooded the yard and ignited in a flash that forced a full evacuation. Fire leapt from tank to tank along a row built for capacity, not safety. 7 tanks were destroyed in the first 3 hours. Operators vented remaining stock to prevent more explosions. Losses topped 300,000 barrels and output dropped by half for weeks. At Ras Tanura in Saudi Arabia on March 3rd, a swarm of drones targeted the North Tank field. Small explosions merged into a rolling fire front, flames moving like a living thing across the yard, driven by wind and leaking valves. The fire burned uncontrolled for 11 hours with secondary blasts as vapor pockets ignited beneath collapsed catwalks. 4 tanks were lost as responders fought to protect the process units. At Yanbu on March 14th, a missile failed to breach the crude tanks but shattered pipelines feeding the hydrocracker. Pressurized product sprayed across the apron, forming a dense vapor cloud. A static discharge triggered a fireball, engulfing 2 tanks and sparking smaller fires in the pump house. The commander called it a race against chemistry. Losses reached 90,000 barrels, and the unit was offline for over a month. Across these sites, the pattern endures: ignition followed by rapid vapor release, and fire spreading faster than systems can respond. The volatile physics of hydrocarbons remain unchanged, leaving scorched tanks and blackened ground, a margin for error as thin as ever. Modern analysts dissect refinery catastrophes using tools that would have seemed like science fiction in Rockefeller's day: satellite forensics, thermal imaging, and real-time data from hundreds of sensors. Yet, when the smoke clears, the patterns they map echo the same old mechanics. In both eras, the core failure is containment. Whether it is a wooden tank sweating naphtha in summer heat or a steel shell breached by a missile, the result is the same: volatile hydrocarbons escape, and the margin for isolation collapses. Forensic teams now reconstruct fire progressions frame by frame, tracking how vapor clouds drifted, where pressure surges overwhelmed relief valves, and how foam reserves dwindled under relentless heat. In Haifa, time to isolation was measured in minutes, but the fire still outran human and automated response, leaping containment berms as if they were not there. At Mina Al-Ahmadi, the foam supply was depleted in under 2 hours, forcing crews to abandon exposed tanks. In every case, remote shutdowns lagged behind the pace of the blaze, crippled by damaged control systems or blocked by cascading failures in the yard. The numbers tell a grim story. Average time from breach to full evacuation has shrunk to less than 15 minutes at many sites, yet fires routinely spread from tank to tank in under 10. Once vapor escapes, the race is lost before it begins. Even the best engineered yards, reinforced concrete, firewalls, and automated suppression cannot erase the basic chemistry. Hydrocarbon vapors still pool in low spots, still ignite with a spark too small to see, still propagate along invisible seams and trenches. Containment, for all its technological advances, remains an aspiration rather than a guarantee. Safety engineers speak of layers of protection, but each layer is only as strong as the weakest link: a stuck valve, a depleted foam tank, a sensor blinded by heat. The same systemic incentives that shaped the 1880s, output targets, cost controls, pressure to keep lines running, still drive decisions today. Risk is distributed across systems, but the consequences converge in minutes. The lesson is not just about old equipment or new threats. It is about the enduring reality that the physics of hydrocarbons and the economics of production continue to outpace the safeguards meant to contain them. In the aftermath, analysts return to the same question workers once faced in the shadow of wooden tanks. How much risk is considered acceptable, and who pays the price when the calculation fails? Today, oil still flows through labyrinths of pipes and tanks, where invisible hazards and split-second decisions shape every shift. Decades later, the same pressures to maximize output, to cut corners, to accept risk as routine, persist in refineries worldwide. Progress remains inseparable from peril when safety is not the priority. As modern infrastructure ages and demand intensifies, the line between innovation and catastrophe grows thinner. The true cost of fuel is measured in lives, not just barrels. Share your thoughts below.